Hi, everyone. My name is Robert Soule. I'm an associate professor at Yale University and a member of the P4 technical steering team. I'm very happy today to introduce Debnil Sur, who is a senior software engineer at VMware in the Research and Innovation Organization. Debnil is currently researching topics in networks and distributed systems, and he's particularly interested in building better tools for programmable networks. Along these lines, he's the primary developer of the NERPA project, which he's going to present today. Previously, he graduated from Stanford University with BS and MS degrees in computer science.
Cool. Thank you so much for the kind introduction, Robert. Hi, everyone. My name is Debnil. I'll be presenting the paper NERPA, Network Programming with Relational and Procedural Abstractions. As you can see, this is a very nice acronym. So in this paper, we introduce a unified environment for network programming. In our proposed methodology, the developer can program all parts of the network, management, control, and data planes with a single set of tools. This automates many parts of how we program the network stack, including data plane programming in P4. Our overall goals are correctness and scalability of network programs. Here at VMware, we are actively developing this and hope to turn it into production-grade software. It's my privilege to work with Ben Pfaff, Leonid Rizik, and Mihai Budiu in implementing this vision. Before diving into the specifics, I'll provide a roadmap for this presentation. I'll first describe the motivating problems behind our work. I'll then explain NERPA system design with a couple of implementation details. I'll close the talk itself with an illustrative example, and finally, I'll take any questions. So to motivate NERPA, let's pose a basic question. How do we program networks today? Typically, you'd separately program the management, control, and data planes. We've shown a picture of a common approach here. The management plane sets high-level network configuration. It's often implemented as an API backed by a database. The control plane controls how data is forwarded throughout the network. It's implemented as an SDN controller written in an imperative language like Java or C++. The data plane processes user traffic. It's implemented using flow programmable switch software or hardware. Now, in our experience, this often creates two types of problems: correctness and scalability. Let's first talk about correctness. Software-defined networking, or SDN systems, are difficult to maintain over time. This can decrease developers' confidence in overall correctness. To understand why, think about the process of programming a big network. The control plane will install programs in network devices, like P4 programs or program fragments in OpenFlow. The controller acts as a specialized compiler, converting high-level policies into these small programs. So what happens as the developer implements features over time? Small programs that correspond to different tables and priorities become scattered across a large code base. It's really difficult to be confident in overall correctness. Consider this example from OVN's NorthD program. The centralized daemon translates high-level OVN configuration into logical configuration for the controller. In 2016, it had about 2,500 lines of code. And at the end of last year, this number had approximately 10x. Examples of this exponential growth abound across networking software. They hurt maintenance, developer confidence, and program correctness. The second problem we'd like to address is scalability. As a system grows, the SDN controller must still respond to changes. This demands an incremental approach for effectiveness. That's because network state often changes frequently in small ways. That's sometimes because of configuration changes in the management plane, but more frequently it happens because of data plane messages, like in Mac Learning. When the network configuration changes, the controller should not have to recompute and redistribute the entire network state. Instead, the amount of computation should be proportional to how much network state is actually modified. This avoids unnecessary and wasteful work, which can have significant performance costs at scale. But writing an incremental controller in an imperative language like Java or C++ is hard. The programmer must either code in an unnatural style or implement ad hoc and fragile support for necessary incremental changes. That's why some of these implementations in Java or C++ become thousands of lines of optimized code. And as we all know, more code means more bugs. It introduces many new sources of errors, and it generally hurts scalability. Along these lines, consider another concrete example from OVN. This graph shows the rate at which ports can be created and bound across 2,000 hypervisors. You'll see that as the number of ports increased, the rate of their addition declined in an exponential fashion. I should note that the context of this experiment is slightly different. It wanted to see at what number of hypervisors this performance became unworkable, and it found a crossover point somewhere between 2,000 and 3,000. But regardless, the examples are still illustrating the important problem. It's hard to write high performance, well-optimized incremental code. And in network systems, we see this downsize at increasing scale. With these classes of mind, we present NERPA, a programming framework meant to address these classes of issues. It's currently a prototype, and we're actively developing it, hopefully into production-grade software. NERPA contains two high-level ideas with significant implications for network programming. First, automatically incremental control planes can directly aid scalability. Rather than struggling with an incremental Java or C++ program, the NERPA developer writes the control plane in differential data log, or DDLog for short. This is a really cool programming language for incremental computation that our team has been developing. In DDLog, you write non-incremental code and automatically generate incremental programs. I'll talk more about this in a couple of slides. Two, the control and data planes are co-designed, which helps overall correctness. The relations for the control plane are generated from the data plane and management plane. This makes common structure across these different parts immediately apparent. NERPA tooling can then automate and simplify data conversion when moving data between the planes. This avoids time you would otherwise spend writing glue code and figuring out interfaces between different software. The developer can instead focus on expressing core network features. These innovations help address both of the above problems. First, how does NERPA address correctness? Well, because we generate relations and create a common structure, NERPA effectively pairs a DDLog control plane with a P4 data plane. This lets us write a complete type check program. This provides more obvious correctness than your typical P4 or OpenFlow-based data plane. While that does have some structure, the controller does not know about it because it's only generating program fragments. But here, the controller can more easily convert data and synchronize state between these parts, as we'll discuss in our design section. Second, how does NERPA address scalability? Well, remember that we had identified scalability challenges, which we could address through incrementality in the control plane. Implementing the control plane in DDLog makes it fully and automatically incremental by design. Let's talk a little bit more about DDLog. This is a system for incremental computation on database tables. You can construct tables or relations, and whenever you hear relation, think table, and vice versa. These tables have a powerful type system and a relational and procedural language for specifying desired computations with granularity. It also has a data flow-oriented system that can allow for performant updates to these relations. So that was a lot of big words. What does this conceptually look like? First, it's organized like a normal data log program, which computes on tables like SQL, takes some inputs, some defined rules, and then maps those to outputs. So DDLog goes a step further, and it computes on changes to those tables. At runtime, a DDLog program accepts a stream of inputs, or rather a stream of updates to input relations. An update inserts, deletes, or modifies some subset of input records. And in response, DDLog outputs an update to its output relations. These strengths are especially well suited for graph computations on networks. This means that a DDLog programmer does not write incremental algorithms. Instead, they simply specify the desired input-output mapping in a declarative fashion. Then the DDLog compiler takes that specification and makes it incremental. As a result, small changes to inputs only trigger proportional output changes as desired. We'll see some examples of DDLog syntax when we walk through our NERPA examples, but for now, just keep these general concepts in mind. So let's talk about NERPA's design as a system. At a high level, NERPA coordinates three pieces of software, corresponding to three classes of computations in the network. First, the NERPA programmer is responsible for providing three programs: an open vSwitch database, or OBSDB schema for the management plane, a P4 program for the data plane, and in the middle, a DDLog program for the control plane. These are not random choices of languages. When working with the control plane, you express state as relational tables such as firewall rules or routing tables. A relational language like ddlog with some procedural abstractions helps efficiently express these concepts. But when forwarding packets, you want something more imperative like P4. We want to provide the right abstractions for these planes within a unified programming environment for both, while working with tools that people are actually using right now in their networks, like OBSDB and P4. NERPA makes it easier to interface between these three programs. It generates code to help move data between the different planes instead of forcing the developer to write glue code. To do this, we generate ddlog input and output relations from the OBSDB schema and from the compiled P4 program. Let's dive into each plane specifically. The management plane is a high-level policy used to set network configuration. As mentioned above, many management planes are implemented as an API backed by a database. Similarly, to configure the NERPA management plane, a system administrator would populate and modify an Open vSwitch database, or OBSDB instance. The database schema models the network entities and their relationships. It's important to note that OBSDB is just an example of an appropriate database. NERPA has no direct relationship with Open vSwitch. And in our case, there are 3 reasons to choose OBSDB. First, familiarity from past work. Second, integrations with the right tools, especially ddlog. And third, OBSDB is well suited for state synchronization because the server tells the client about changes to a database. Another database with the right integrations that operates on changes could be just as effective. Next, the control plane controls how data is forwarded throughout the network. The NERPA programmer can define core network features through ddlog rules, which compute incremental changes to the data plane based on input changes in network configuration. It takes 2 types of input relations. One represents administrative changes in the network config. It synchronizes these changes from the management plane. 2 represents messages from the data plane. These are converted from packets, digests, and other notifications. The output relations are generated from the data plane, and as a result, their structure directly maps to a P4 match action table. The control plane also sends network state back to the management plane, which can help dictate additional configuration changes. Finally, the data plane processes user traffic. We program this with a P4 program. The NERPA controller gets output from the control plane, and these outputs represent new, incrementally designed table entries for the P4 switch. The controller then converts those into the format of P4 table entries. It installs them in the P4-enabled switch through the P4 runtime API. So that was a lot of individual information. Let's see how these pieces fit together. At a high level, this is how information flows in NERPA. At the top, you'll see 3 highlighted boxes. These represent the files that the NERPA programmer must supply: the OBSDB schema, the ddlog program, and the P4 program. In our prototype, the management plane is an OBSDB instance. Its schema is used to initialize and run an OBSDB server. The admin user interacts with that database and changes high-level network configuration. These changes are then communicated to the control plane program as input relations. Remember again, OBSDB is a placeholder. It can be any database of your choice with the proper integrations and handling of changes. ddlog relations are generated from the OBSDB schema and the P4 program. The user writes the ddlog program that connects the relations using rules. That program is then compiled and actively runs as the control plane. You'll see that we've also called this box state synchronization. The control plane program should be embedded in a larger piece of software, which leverages NERPA tooling to convert ddlog relations to and from the appropriate types in the management and data planes. It should also coordinate moving this data between the planes. Finally, using the P4 program, we program a network device like a flow-enabled software or hardware switch. This receives P4 table entries from the state synchronization program, which are converted output relations. It also sends data plane notifications, like digest messages and packets, back to the controller to synchronize state. Those are converted into input relations from the control plane program. This shows how all of these pieces fit together. So far, we've talked about our high-level design and some highlights of implementation. Let's walk through a specific example to see how these pieces can fit together. We've implemented a simple network virtualization switch, or SNVS, which includes things like VLANs, MAC learning, port mirroring, and similar core network features. It's pretty straightforward. It's used in the integration test in the NERPA repo, and it showcases the core benefits explained above. So let's see what the code looks like for VLAN assignment. Don't focus too much on reading every single line of code. The high-level takeaway is how one program turns into another. I've added some highlighting, which hopefully helps. First, we generate the output relations from the P4 table using P4 info to ddlog. This is a tool that we wrote. It takes the P4 info file, which is outputted by the P4 compiler. That's just a file that contains a bunch of binary information about how the P4 program looks when compiled. The left side of the slide has a P4 match action table, and the right side has a ddlog output relation, which is generated by the tool. You can see the common structure that lets output relations be easily converted into table entries. P4 actions are converted into an enum and ddlog. We've annotated the keys in the P4 table with the names. Those names are then used for fields in the output relation. And the output relation also includes the priority and the action, so it can be easily converted to a table entry. Next, we generate the input relation from the OVSDB schema using OVSDB to ddlog. This existing tool was created by ddlog developers for its use in OVS. The left side of the slide has a small table schema, and the right side has the generated ddlog input relation. You can see that columns are directly mapped to fields in the input relation, and type information from the schema is directly converted accordingly. We also have an automatically generated UUID in the OVSDB database, which is part of the input relation and its primary key. Finally, let's put those input and output relations together in a rule. You can see this data log-like syntax shows we are computing the input from the output from the input. We extract certain fields from the input relation and then use them to define variables and pass to the output relation. This particular output relation sees if it was told about a port with a particular tag. If so, it computes an output relation that sets the VLAN ID to that tag. So what does this output relation actually say? If a packet came in on the provided port, but it didn't have a VLAN, the VLAN ID would be set on that packet to match the value from tag. It would get installed as a table entry with priority 1 as per this rule. In conclusion, we hope you agree that relational and procedural abstractions in combination can improve correctness and scalability. In NERPA, these combinations occur at many different levels. OVSDB is relational, ddlog is mostly relational with procedural components, and P4 match action tables are relational, while packet processing is procedural. These abstractions combine in beautiful and complex ways to make it generally easier to program a performant and scalable network. You can check out our prototype on GitHub, and in future, we plan to implement more complex networking features. Since everything is open source, we would love your help. Thank you so much for listening, and I'm happy to answer any questions you might have.
Hi, Debnil. Thank you for the very interesting talk. I really like the direction of this project. Let me ask you a couple of questions. First, I've seen data log used in the past for several different types of use cases. I've seen people propose it for using with compiler optimizations or for building distributed systems. And there always seems to be this trade-off between sort of the conciseness of expressing your logic in these nice logical rules versus maybe someone's comfort with, I don't know, a general purpose programming language like C or something like that. And so I think in some applications, there's been a resistance to using, say, data log rules. Do you think that, do you have any ideas why data log might be, say, a good choice for use in data plane programming in particular? Or is there anything about data plane programming that would lend itself well to using data log formulations?
That's a great question. I'll acknowledge up front that we have seen some impedance when in other projects at VMware, programmers have attempted to use differential data log. And part of that is directly because of these sort of impedance problems that you allude to. It doesn't look like C or C++ or Java. It's definitely a different formalism for how you think about problems. I think the core response to why this is useful for control plane programming is because in the NERPA framework, what we do is we try to make the data log rule as simple as possible. So what that means is that we say the output is directly from P4, which is a language that many people are using. And we say that we generate the input relation directly from your database schema for the management plane. This means that all that the user ultimately has to do is look at the generated inputs, look at the generated outputs, and say, how do I actually compute one rule from another? Basically, we take the difficulty, which we've noticed, which is how do I actually form this problem, right? And instead we say, okay, you've written other programs that can be used to generate and form that problem at a high level. All that you have to do is make that connective piece in the middle. And writing the rules seems like the generally easiest part of programming for most of the programmers when first introduced to data log, because that's just computing input-output relation. It's just expressing a concept in a very direct way.
So from what I understand is that a user of NERPA would run a tool on, I think, the database schema, and then they would run a tool on the P4 program, and they would get some output of that, which then they could combine, and they would be responsible for writing the ddlog program that would sort of map sort of from the management to the data plane. And I'm wondering is where you feel the right level of abstraction is. So I didn't get a sense from the presentation of what's the level of abstraction that you're aiming for when a user writes a differential data log program. Is it sort of is the goal to write in sort of high level intents, or is it more like a lower level, like control plane programming, like might be useful with like open flow style specifications?
Yeah, that's a great question. The goal is for them to just be able to write high level intent. And as you notice, that might require additional programming language support at some level or another. The way we plan on bridging this is sort of in two ways. The first is by encouraging a lot of complex pair packet processing to ultimately be done in the data plane using P4, because we think that's the more appropriate site for a lot of this to happen. And we want to encourage developers to think, okay, let me process that packet in an imperative fashion in P4, and then just think, what's the high level intent of the networking feature that we want to enable? There's a couple of other places that you could push those implementation details for sure. One of them can be by encouraging more complex data log programs as well, as you alluded to. I think this does require some more work on the programmer part, and to assist that, we want to put as many examples as possible in the NERPA repository so that developers don't get caught up with that as a stumbling block, which would otherwise be really understandable. And the other thing that's really interesting is using it to plug into other networking programs. So for example, my colleague Ben will be talking about leveraging some of these tools to be able to use a high performance open vSwitch switch as the backend for a P4 program. We think that some of the tools that we presented allow for easy data conversion between existing software that everyone might be using. And so we think that's the ultimate benefit of a lot of the tools we presented today.
I see. So I'll just wrap up with one last question is, I know you have a proof of concept available on GitHub. I'm wondering, in your experience, so what type of correctness properties have you been able to check or guarantee using NERPA? Could you give some examples of, I don't know, maybe errors that you found in network configurations?
Sure, that's a good question. I think the sorts of correctness problems that we've seen are less that of difficulties in network configurations and more as your system is trying to scale over time, what are the sorts of bugs that might arise in how other larger pieces of software have programmed, or other bugs that they've encountered that could have been solved by just having a high level specification for the control plane. So more to your point, I think formal verification of NERPA programs as a whole is something that's definitely on our roadmap. But one of the things that we've found by talking with a lot of network programmers who, including people on our team who have attempted to write these sorts of incremental programs over time, are just corner cases, edge cases, and the like that arise as they're attempting to write incremental code. And the goal with high-level specification is that you would avoid those sorts of things altogether. So that's the more general, I think, answer to your problem, to your question. I think as we move forward, we want to do sorts of formal verifications to be able to look at these are specific bugs that you might have had that we want to be able to address. But at a high level, I think the point that we want to get across is that encouraging high-level specification of control plane rules can help avoid corner case bugs that might otherwise come up.
Okay, thank you again, Debnil, for the very interesting talk. I think this sounds like a very exciting project. I'm looking forward to checking out the GitHub repository.
Awesome. Thank you so much for the great questions, Robert.